Welcome to our last section of Chapter 7. 7.7, Fluid Pressure and Fluid Force. Okay, pressure is the force per unit of area over the surface of the body. So that's our pressure. Ever been jumped in a pool, gone down 8 feet, and you feel that pressure? Your ears are really sensitive to it, so you feel it mostly in your ears when you do that. Definition of fluid pressure. Pressure on an object at depth h in a liquid is pressure equals P, which is W times H. W is the weight density of the liquid. We typically use water, but we could be talking about something else, talking about gasoline, talking about oil, different things that have different densities. Okay. So ethyl alcohol, 49.4, gasoline, 41.0 to 43.0, depending on the type of gasoline, the octane, and the temperature. Glycerin, 78.6, kerosene, 51.2, mercury, 849.0, but do not dive in a pool of mercury, really, really bad for you. Seawater, 64.0, and regular water, non-salt water, 62.4, as we saw earlier. And I think it was 7.5. Pascal's principle, the pressure exerted by a fluid at a depth h, let me get this diagram up here, is transmitted equally in all directions. It's kind of a hard concept to wrap our minds around, that you got like a plate in the water and the pressure coming this direction, same as the pressure going that direction, same as the pressure going this way. But think of it like this. Once you're in the water at this depth, you got water pushing up on you and pushing down on you and pushing sideways. But I mean, it's pushing up and down, so you're getting pressure from both sides. So the pressure is the same at the indicated points. The same here, here, here. The area of the top side of a piece of sheet metal is 16 square feet. The sheet metal is submerged horizontally in 5 feet of water. Find the fluid force on the top side. So imagine a tank of water. That's the universal symbol for water there. Little waves. Okay, so we have a tank, piece of sheet metal. Let's say it's a square. And that's 5 feet down. We use all 4 colors in this problem. Okay, so what is the force on this? Or what is the fluid force? So the force is going to be the pressure times the area. So we're in water, we do 64.5, or sorry, 62.4, times the 5 feet down, times the 16 square feet of the piece of sheet metal. So we have 3 components here. Water density weight, depth, surface area. This comes out to be 4,992 pounds of pressure on this 16 square foot piece of sheet metal. Now, this is a horizontal one. We're talking about, it's horizontal, it's not vertical, it's not slightly vertical, it's horizontal. So pressure from down, or sorry, from on top and from below, okay? If this was vertical, you have a different story. In example 2, find the buoyant force of a rectangular solid of the given dimensions submerged in the water so that the top side is parallel to the surface of the water. The buoyant force is the difference between the fluid forces on the top and the bottom sides of the solid. So we have this figure, it's 4 feet tall, so the difference on top and bottom is 4 feet. We can assume this is going to be, doesn't look like it's not drawn to scale by any means. This is 6 by 8. So the depth from the surface down to the top of this is h, and from the top of this object down is 4, bottom of the object. So the overall depth from the surface all the way down is h plus 4. So the surface area of the top. And the bottom. They're the same because it's a rectangular solid. It's going to be 6 times 8, which is 48 square feet. Is this feet? We'll go with feet. So the force is going to be the bottom force minus the top force. So that's going to be 62.4 times h plus 4 times 48. So water's density, the depth, surface area of the bottom, minus 62.4 times h times 48. This works out to be 62.4 times just 4, because you're 62.4 times h times 48, that's the same thing as area subtracting, times the 48, and we have 11,980.81 pounds. That's the force on this object. And the idea is, though, is that it's buoyant, so it means it's not going up or down, it's stationary there. It's the point of buoyancy. Okay. Now let's talk about something that might be a variable force. And you see in this example we're going to do in 3, we have this triangular piece going with force on it. It's going to be greater force down below than up above. So you have it vertically exposed to water. Okay, the force F exerted by a fluid of constant weight density, W, per unit volume, against a submerged vertical plane region from y equals c to y equals 0. Force to be the weight times the limit is, our norm goes to 0, I equals 0 to an n of h of yi times L of yi delta y. In terms of what we're used to, W integral from c to 0, not 0 to c, c to 0, from the deep point to no depth at all, h of y, L of y dy, where h of y is the depth of the fluid at y, L of y is a horizontal length, so our cross-sectional length of the region at depth y. Excuse me. Okay, so let's take our little shape here. We have let's find the fluid force on the vertical side of a tank where the dimensions are given in feet. Assume the tank is full of water. So you have this kind of a triangular prism full of water. What's our force on the side of this going to be? So we have a side of a tank. You're going to have some kind of a cross-sectional, think of that bar with height dy, or call it delta y. Now how deep is this going to be? That's going to be at 3 minus y. So if y is 3, it's not deep at all. If y is 0, it's down to 3 feet deep. What would that width be described as? Well, if we break this down, the whole thing across is 4. If we just go halfway across, this is 2 and this is 3. So that this side could be described as rise, let's see, how should we state this? I want to say rise over run, but I think that's not going to be appropriate. No, it's going to be, to get to this point, y equals 2/3. I'm sorry, not y equals. It'd be just 2/3 y. That is saying that it's going out 2/3 of what it's going up high. Okay. So that would describe this side over here. Now, that's the width. That describes the width. That's our width there. For that half, we have 2 halves to this. So 2 times 2/3 times y is going to be 4/3 y, and that's the overall width. Okay. If you want to describe this the other way around, y equals rise over 1/3 x multiplied by 2/3 gives you 2/3 y equals x. And so we're talking about it changing vertically, so we have to have it in terms of y. Okay. So we have L of y, we have h of y. We could put this together. Force is going to be 62.4 times the integral. And this is the one that's above the surface of the ground, supposedly. We're going to define it to be above, so we're going to go from 0 to 3 on this. Versus being below the surface, you go from the value up to the height, up to 0. We have 3 minus y times 4/3 y dy. That's going to be 4/3 times 62.4, integral from 0 to 3, of 3y minus y squared dy. So that's going to be 4/3 times 62.4 times 3y squared over 2 minus y cubed over 3 from 0 to 3. That's 4/3 times 62.4 times 3 times 3 squared is 27, so 27 halves minus 3 cubed is 27, so 27/3 minus 0. You get from that 374.4 pounds. That is the force on this side of the tank. So again, it varies. There's going to be more force down here at any given point, but it's wider up there, but the overall force is 374.4 pounds. So I just want to state again how we come up with this width. Now, this is in terms of y because we're talking about changing vertically. If it was in terms of x, it'd be y equals 3/2 x. Multiply by the reciprocal, solving for x, 2/3 y equals x. That's why it's 2/3 y. Okay, let's go on to the last example from this section. A circular plate of radius r feet is submerged vertically in a tank of fluid that weighs W pounds per cubic foot. So we have this plate in this water, in this fluid. Okay. The center of this circle is K, where K is greater than r, feet below the surface. So this is definitely below the surface. There's some distance between the top of the circle and the surface. Show that the fluid force on the surface of the plate is F equals WK pi r squared. So evaluate one integral by a geometric formula and the other by observing that the integrand is an odd function. So let's put this together. There we go. So top of this plate is R. The bottom of the plate we'll call negative R. We'll set up a little axis system here. Okay, our height here, h of y, is going to be k minus y. The question is, what would we define this to be, the width of this? Let's think of it this way. I'm going to go back to a different color here. We know that for a circle, center at 0, it's x squared plus y squared equals r squared. And we want to solve for x squared equals r squared minus y squared, and x equals plus or minus the square root of r squared minus y squared. We're not so worried about, we want both sides, but let's think about the one side. This one side is defined by x equals the square root of r squared minus y squared. So the whole thing, our L of y, would be 2 times the square root of r squared minus y squared. That's double that. So our force is going to be W times the integral from negative r to r of k minus y, that's my h of y, times 2 times the square root of r squared minus y squared dy. And again, think of this as delta y becomes your dy. Okay, so our force is going to be W times integral from negative r to r of 2k times the square root of r squared minus y squared minus 2y times the square root of r squared minus y squared dy. So our force is going to be, I'm going to break this into two integrals. 2k can come out, 2kw, integral from negative r to r of the square root of r squared minus y squared dy. Then we have minus w times the integral from negative r to r of 2y times the square root of r squared minus y squared dy. Okay, a couple pieces here. This is the area of half a circle. This is an odd function. Now, being an odd function from negative a to a, or in this case negative r to r, means it's going to be 0. So if we did the negative w times the integral negative r to r of 2y times the square root of r squared minus y squared dy, that's just 0. I should say, I really want to stress that it's this half. This half is just equal to 0. This half, being a circle, is going to be 2kw times pi r squared over 2. And minus the 0 over here. 2's divide out. Force is equal to kw times pi r squared. And that's what we're supposed to show. So we took advantage of the fact that this is an odd function going from negative a to a, so that's 0. This is the area of half a circle. That's going to be pi r squared over 2. Multiply that by 2, we get this. That's the end of this section. Wow. End of this chapter too. So we'll stop there today, and I will see you guys on our chat session. Thank you.